We are often astonished to find why the Leaning Tower of Pisa is still leaning and has not yet fallen. Why we find it difficult to balance a stick upon our fingers. But Nick Valenta can cross the Grand Canyon walking on a wire. In all these examples, equilibrium has a role to play. So in this video, we will be learning about equilibrium and the principle of moments. Gravity pulls a tennis ball down, but an equal and opposite normal reaction force causes it to remain at rest. This state in which a body remains at rest despite the action of several forces is called static equilibrium. When a skydiver jumps off a plane, he accelerates to the ground due to the force of gravity. But an equal and opposite force of air resistance makes him drop at a uniform velocity. This state of bliss is also on account of equilibrium. When a body moves at uniform velocity, despite the action of several forces, it is in a state of dynamic equilibrium. But a body needs much more than that to achieve a state of rotational equilibrium. Let's consider this plank, which is balanced using a fulcrum or a pivot or a trestle. We now have two apples on either edges of the plank. One of them weighs 2 Newton and the other weighs 4 Newton. Each of these apples is at a distance of 100 centimeters from the fulcrum. In this case, the sum of clockwise moments is equal to minus 4 Newton meter, and the sum of anti-clockwise moments is equal to 2 Newton meter, and hence the resultant torque is equal to minus 2 Newton meter. So what happens? This plank has a clockwise moment and it will tip towards the right. However, if we shift the bigger apple towards the left such that it is at a distance of 50 centimeters from the fulcrum, the sum of clockwise moments would be equal to minus 2 Newton meter, and the sum of anti-clockwise moments would be equal to 2 Newton meter. As a result, the net torque would be 0. So what would happen? The plank would balance again, despite the fact that both the apples are at different distances from the fulcrum. Here, the sum of clockwise moments is equal to the sum of anti-clockwise moments. In other words, the net torque is 0. This is called the principle of moments. Now here, the downward force on the plank is equal to the weight of both the apples, which is equal to 6 Newton, and the upward force acting on the plank is the force exerted by the fulcrum, which is equal to 6 Newton. So what we can say that for an object to be in equilibrium, the resultant force on the object must be 0, and the resultant torque on the object must also be 0. So the next time you want to balance a seesaw, you know exactly what to do. And now, the summary of this video. A body is said to be in equilibrium if it is in a state of rest or uniform velocity. Static equilibrium is a state of rest despite the action of several forces. Dynamic equilibrium is a state of uniform velocity despite the action of several forces. In equilibrium, the sum of clockwise moments is equal to the sum of anticlockwise moments. This is also called the principle of moments. When a body is in equilibrium, the net force as well as the net torque acting on it is zero. So that's all in this video. In the next video, we will explore the exciting concept of the center of gravity.